Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. Let's get started. So we were doing this, studying this algorithm for predicting election outcomes based on sampling, and we described the algorithm in our last lecture. It's very simple. You just sample L votes uniformly at random with replacement and output the majority of those sampled votes. That's it. And the question that we are concerned with was how many votes we should sample to have, say, 90% chance of our prediction being correct. So let's see how we do this. So let's do the analysis. So suppose we have capital N number of voters. We have two candidates, two parties, say A and B. And if a fraction of votes, A gets FA fraction of votes and B gets FB fraction of votes, and without loss of generality, we may assume that FA is greater than FB. Let's assume there is no tie. Okay. And let f hat A be the number of votes, f hat A times L be the number of votes for A in the samples. We have L samples, and that among those L votes, f hat A is the fraction of votes that A gets, and similarly f hat B times L be the number of votes that B gets. Sure. And and here is the observation is what it is, that if algorithm outputs correctly if f hat of A is more than f hat of B, right, because that's the truth. Sure. So now we will study what is the probability that the algorithm does not output correctly. So probability that the algorithm outputs wrong answer is the probability that is a probability that f hat of A is less than f hat of B. Yeah, feel free to stop me and ask questions whenever you have doubts. It's not very difficult. Okay. Now we want to simply study this probability. Fine. Okay. So this is probability that yeah. So f hat of A, sorry, f hat of A is less than f hat of B, same as saying f hat of A is less than half, isn't it? Because f hat of A plus f hat of B is 1. Okay, now so we want to study this event. So to study this event, again we want to use those Chebyshev's inequality and those kind of things. For that we need random variables, and here is how we do it. Okay. So let's define following random variables. Following random variables, what are they? So xi, we define it to be 1 if so we have sampled L votes. Let's call them vote 1, vote 2 up to vote L, and you define a random variable xi to be 1 if the ith vote happens to be for A, and otherwise you define it to be 0. This is for I in L, for all I. And we define x to be the number of sampled votes for A. So you have sampled L votes, and x denotes the number of votes in the sample which is for A. So we can obviously write x equal to f hat of A times L, because that's how f hat of A is defined. Whereas on the right hand side, we can write this as summation of x1 plus x2 xl. Sure, because each xi takes a value 1 if the ith vote goes to A, otherwise it is 0. So we get this equality. And now to apply those concentration bounds, we need to compute its expectation of x and variance of x. Sure. Yeah. So what is expectation of x? We have expectation of x is right, and now we apply linearity of expectation to push this expectation inside. Sure. And now we will just compute the individual expectation of xi. So what is expectation of xi? That's very easy to compute. So xi takes value 1 with probability 1, xi equal to 1, and then value 0 with times probability xi equal to 0. So, the second term vanishes and the first term is only probability that xi takes value 1. Can anyone tell me what is the probability that xi takes value 1? Sorry, it is FA, because FA is the fraction of votes for A. So, it is the probability, FA is the probability that xi takes value 1, FA. Good. Okay. And and so what we have is that expectation of x from this line, we add FA L times and we get FA times L. Sure? Please stop me if you don't follow any step. Sure. So, we have computed expectation of x. Why we are computing expectation of x? Because x is f tilde a times L. L is some fixed number, whereas f tilde a is the quantity that we want to f tilde is the quantity that appears in the event whose probability we want to compute. So, f tilde a is directly related to random variable x, and that is why we are computing expectation of x, and now we will compute variance of x. Make sense? Okay. Now, let us compute again variance of x is variance of and now again look here we will be crucially using the fact that our sampling is with replacement. That means all these x1 to xl are independent because they are drawing a uniform sample from the same bag. And since x1 to xl are independent, this variance also we can push inside, like linearity of expectation. If it was not independent, then we couldn't have done this. So, this is so now it boils down to computing variance of xi. So, let us compute variance of xi. So, I in L so this is expectation of xi minus expectation of xi square. This from the definition of variance, and we have already computed expectation of xi, that is f of a, f a. So, we put that f a here whole square. And now what? Now xi takes value 1. So, this 1 times probability that xi takes value 1 plus sorry this is square xi takes value 0. Sure. And now we will just put those numbers. What do we have? Xi takes value 1 with probability f a, and this you have f a square, and xi takes value 0 with probability f b, which is same as 1 minus f of a, f a. Sure. And let us do it. Now, let us expand, some things will cancel. It is 1 minus twice this FA cube getting cancelled, so we have FA minus FA square. Isn't it? And so this we can write as FA times 1 minus FA. Can you tell me which value of FA maximizes this term, maximizes this quantity? Remember that FA is in between 0 and 1. So in this range, what value of FA maximizes this quantity? Half. It's elementary calculus from 12th standard. So let's put half here, and so we can write this is 1/4, less than 1/4. Sure. So we have an upper bound on variance of xi. Now we can use this upper bound to upper bound the variance of x. So what we have is that variance of x is less than L by 4. Sure. And now we have all the machinery, and we will simply apply the Chebyshev's inequality. Now recall what we want to compute. We want to compute the probability that f tilde a is less than half, right? This probability we want to compute because this is the error probability. Now to match up with x, so what is the relation of f tilde a and x? F tilde a times L equal to x. So let's multiply both sides with L, and now the left hand side is x. For x we have already computed expectation and variance. So what it is? Probability x is less than L by 2. Okay, very good. And now we want to apply Chebyshev's inequality. So right hand side we should write as say c times some constant times square root of variance. But we haven't computed exactly square root of variance, we have an upper bound. So let's leave it as square root of variance. So let's write this way. Sure. And treat this term as c. This particular thing as the cost as a c in the Chebyshev's inequality, and apply Chebyshev's inequality here. Let's see what we get is Chebyshev's gives is that less than equal to this square c square means L square by twice, no, not twice, 4 times. Sure. You recall Chebyshev's inequality? It was 1 by c square. Yeah. Oh yeah, correct. That's why it is not coming here. Yeah, x minus expectation of x was there. So let's remove this term first. Yeah, there was x minus expectation of x. So let's subtract expectation of x from both sides. And this is then less than L by 2. And what is the expectation of x? It was FA times L. Sure. Okay, and now and again there was a mod there, so we have less than equal to probability that mod of x minus expectation of x, or yeah, and also in Chebyshev's inequality this was greater than equal to. So let's put left hand side to right hand side and right hand side to left hand side. So this is probability that expectation of x minus x is greater than f a minus half times L. Sure. And now there was a mod. So again you can put the mod. So this is less than equal to probability of mod of you can put mod on both sides. Can anyone tell me why I can't write equality and I have to write less than equal to here, this thing? Yeah, exactly. So the blue event, so this event is actually a superset of this yellow event, right? So this yellow event looks like this and the blue event is here. Blue event implies yellow event, not the vice versa. That's why I get this less than equal to. Okay, now we are in a Chebyshev's form, and no, not exactly in the Chebyshev's form. So let's continue, uh, because we need to write in terms of variance. Let's do it. Do that. Okay, I can simply remove the mod on the right hand side because we have assumed to begin with that f a is more than f b, so that means that f a is strictly more than half. So let's get rid of the mod sign, f a minus half, and write it in terms of variance to apply the Chebyshev, and for that we divide by variance of x, square root of variance of x. Sure? Sure. And now we apply the Chebyshev's inequality, and this is treat yeah, treat this particular quantity as your c, like in the Chebyshev's inequality, and this is 1 over c square. So its variance of x by f a minus half square times L square. Sure. So this is my error probability, and what is my goal? My goal is to make the error probability at most 10%. So if I choose my L in such a way, so let me write. So choose, yeah, no, not this. Choose L such that the above quantity is at most 0.1. Then by putting appropriate value of L, my error probability, what we have shown, this analysis shows, is that the error is at most 0.1. That means success probability is at least 0.9. So now let's see what L we should plug in. So that's just back calculation. So we want variance of x this to be less than equal to 0.1, and we have an upper bound on variance of x. What was the upper bound? It was, where is the upper bound? Yeah, variance of x is less than equal to L by 4. So let's use that upper bound. So variance of x is less than equal to L by 4. So let's put L by 4 here. Then we get 1 by 4 fa minus half whole square times L. Sure? Variance has an upper bound L by 4. I just put L by 4 there. And I just want to ensure that this, so yeah, write this way. So choose L so that this inequality holds. So what we have is that from these two, that 1 over 4 times fa minus half whole square times L. Yeah, question? Yeah, L by 4 is an, yeah, correct, yeah, sorry. L by 4 is the upper bound only, correct. Yeah, so, yeah, that's right. This is not right. Okay, yeah. So let's see what we have. So we have that variance of x minus fa minus half whole square times L square. It's a L by 4 is the upper bound, so this inequality should go this way. So and we get 4 times fa minus half whole square times L. Fine, because variance of x is less than equal to L by 4, and that we just put here. Now, so maybe we should write here that this one to choose. So this we haven't chosen yet. Now the idea is that, so we don't exactly know what is variance, but we know it's upper bound, and if we ensure that this upper bound is less than 0.1, then this particular quantity is also less than 0.1. If we can show, so if we can show that this is less than equal to 0.1, then this will imply that this particular quantity, variance of x by this thing, is also less than 0.1, and this quantity is actually the error probability, exactly the error probability. And so we want to ensure this. Sorry. So we want to ensure this inequality. Ensure this, and so to ensure this, what L we need to choose? We need to choose so that this happens. So 1 by 4 fa minus half whole square L. This is L is greater than 2. So 5 by 2 . So this is the main result. So this shows that if you L was your sample size, L is the number of samples you draw, is at least 5 by 2 times fa minus half whole square, then the probability that your algorithm makes the right prediction is at least 90%. And also what it shows is that it does not depend on capital N, the size of the population. Not only that, it depends on what? It depends on two quantities. One is what success rate you want. So, for example, if you want to reduce this error probability from 1/10 to 1/100, then your L will also increase. So, maybe we should write in terms of delta. So, if you want your error probability to be at most delta, that means 1/4 less than delta, then you will require L is greater than equal to 1/4 time delta. Sure? Yeah, this is a square term. No, with delta there is no square term. No, L. So there was a now in variance you put for 1/4 L, so 1 L gets cancelled. Sure. So your sample complexity, sample size is also called sample complexity, depends on two things. One, on your error probability that you can sustain, and how close is your election. So if the election is really close means the margin is very narrow. That means if FA is very close to half, then your sample complexity increases, and if FA is away from half, it's then your sample complexity reduces. And FA is away from half means that FA is say 0.7 or 0.8, then that means that means one candidate A is getting much more votes than majority, and FA is close to half means that the winning candidate gets close to 50% votes. That means the losing candidate is also getting close to 50% votes. That means the margin in the election is narrow, and if the margin is narrow, then your sample complexity also increases, because in that case FA minus half will be small and it is in the denominator, so sample complexity increases. So sample complexity depends only on two things. One is the margin in the election and what error probability you can sustain. Question, yeah. It has to be exactly. Yeah. That's a very good question. So for example, to implement that algorithm, I need to put the value of L, right? I need to tell how many samples you need to draw, and this analysis shows is that the number of samples to know what should be my sample size, I need to know FA. And if I know FA already, then why I am doing this thing? Because I know then who is winning. And so this sort of algorithm assumes that you have a guess of FA. You don't know FA, but you know a lower bound of FA, or you approximately know FA, and these sort of things. But that's a very realistic, important question. And these are subtle reasons why. Okay, you can ask if it is so easy math, then why predictions are failing? Why different news channels have different predictions? If it is so easy to calculate how many samples to draw, because of these things. You don't know FA. Various people have various ideas about FA. Based on that, they decide sample size. Other than that, there are various other practical issues also. Here we assume that we can pick a random voter, uniformly at random. How you do that in a practical scenario is often difficult, because in practical scenarios you ask some people, you hire some people who will do the survey for you, and they will go to cities and those things, or places where it is convenient for them to go, other than sampling uniformly at random from the entire population. That's one thing. Second thing is that again we assume that we can sample a vote, and we can ask the voter, whom do you vote, and he or she will immediately tell truthfully. In practical scenario, he or she may not tell. Even if he or she tells, it may not be truthfully. He or she may lie. So there are various other practical scenarios which I am hiding under the carpet behind this nice math, and these are the reasons for which various opinion polls vary. Some fail, some agree. Yeah. But the important takeaway is that the sample complexity does not depend anyway in the population size. Does it seem counterintuitive? How many to you seems counterintuitive? Yeah, this seems counterintuitive. It means, okay, of course in math we can do this. Math shows, but math is not giving me intuition why it is happening so. So let me give you some intuition why it is happening so. So basically, just observe what you are doing when you are sampling a uniform vote. It's like you are think of a bag, a black bag, and within that bag there are two kinds of balls. One is red ball, another is a green ball, and you want to estimate what fraction of balls are red. You want to know whether red ball is the majority or the blue ball is the majority. That's the basic problem, right? And what is and every time you draw a ball uniformly at random from the bag, you are basically sampling from a probability distribution. That you draw a red ball with probability, say f red, the fraction of red ball it has, and the blue ball you draw with probability the fraction of blue ball it has. So for example, if the bag contains 10 red balls and 100 blue balls, then the probability of drawing a red ball is 1/10. On the other hand, if the bag has say 1000 red balls and 10,000 blue balls, the probability remains same. You draw a random ball and you see a red ball with probability 1/10. So what matters is the relative ratio, what fraction of them is red, what fraction of them is green. It doesn't matter how many balls are there in total. Now, does it give little intuitive? Because all it depends is that so you can think of you want to guess the probability of drawing a red ball, isn't it? Isn't it? So, and that probability does not depend on the total number of balls. It only depends the relative ratio of red ball and green ball. If it is 1:10, it doesn't matter if the total number of balls is 1000 or 10,000 or 1 billion or trillion or simply 11 or 10. Because all you want to do at the end of the day is to try to estimate, try to predict, or try to predict the probability of drawing a red ball. And the more better you can do the prediction, your prediction is better. Sure. Now, does it look little intuitive now? Why it does not depend on the size of the population? It only depends on the relative ratio, and it's also reflected in the sample complexity. Look at in the sample complexity, we have FA here. FA is nothing but the ratio of red balls with all the balls. Yeah, question. Yeah. No, because so for example, okay, let me rephrase your question. Let me see if I understand correctly. So your question is that, okay, so can we have another upper bound on this term which does not depend on FA, only depends on delta? Maybe it's a loose upper bound, but it still guarantees that, okay, you take this much samples and you're fine. But so think of like this. So for example, if you say that if L is say greater than equal to say, I don't know, this is upper bound and maybe 10 to the power 100 times 1 over delta. It's much more, but it does not depend on FA and it only depends on delta. So tell me how much error you can sustain, and this number guarantees that you do take this much samples and you are done. Can anyone suggest why such an upper bound cannot exist? Why we cannot hope to prove such a lower bound? Sorry, yeah. Think about it. If there exists, if one able to prove this kind of lower bound, then won't it contradict the line above? Won't it contradict the red line, this line? Because look at Fa minus, in the denominator it has Fa minus half, and by choosing Fa arbitrarily close to half, you can make the right hand side of this inequality as high as possible. So just choose Fa to be closer to half enough so that it is more than the constant below, more than this constant, isn't it? So it doesn't matter how large a constant you can put here, it will always contradict the above line. So you cannot hope to get such result. Yeah. No, there is only one bag. Yeah. No, so either yeah. So if you want a country-wide result, then think of country as a one bag. Yeah. Don't do a state-wide sample. If you want to know who gets what percentage, which party gets what percentage of votes across the country, then think of country as a whole bag and different party has different color balls. Yeah, exactly. It's like presidential election. It's not like the political district-based parliamentary election that we have in India. It's not exactly that, because it depends. So in this case, one can lose even if he gets more than 50% of the votes, because where he is winning, maybe he is winning by huge margin, where he is losing by a narrow margin. So it's possible that one candidate or one party gets 60% votes and still loses most of the seats. So we are not considering those kind of elections here. Yeah, it can be. Yeah, it can be generalized to more than two candidates, and it is again a very nice exercise to show that with the same number of samples. So if you have, say, here we have two parties A and B. If we have 10,000 parties, then also this number remains same. It also doesn't depend on the number of candidates, which is really amazing and which is little non-trivial analysis. Let me not do it here. You can take it as an exercise. If you do usual, so there is something called union bound, and if you simply apply that union bound, you will get another log m term. But it's possible to get rid of the log m and you can have only this term. No, so the FA for the winner. So okay, yeah, that's the right question. So her question is that what will be the denominator? So let me write the result without proving it. So let me write the theorem without proving it, because I need some more machinery for proving it, and I am happy if you are convinced that it shouldn't depend on population size and this for two candidates. Yeah, but let me write the generalized theorem. Suppose we have, say, m candidates. What is that m candidates? Say, I don't know, A1 to AM and n voters, and Fi is the fraction of votes AI gets. Sure, Fi is a fraction of votes that candidate AI gets, and without loss of generality, suppose AI wins and A1 wins and A2 is the runner up. Sure. Then the sampling based algorithm succeeds with probability at least 1 minus delta if L, which is the number of samples, is greater than equal to 1 by, what was that, 1 by 4, it was 5 by 2, no, 1 by 4, yeah, 1 by 4 times it is A1 minus A2 whole square times yeah, F1 minus Fa, yeah, sorry. So it all boils down to margin of victory. What is the margin of the election, and this dependence on delta, this analysis shows 1 over delta again by using a stronger inequality called Charnoff bound. We have used Chebyshev's inequality here. There is something called Charnoff bound which gives stronger bounds. If you use that, you can make this 1 over delta, to log 1 over delta. You can further reduce it. But yeah, so if your sample size is at least 1 minus Fa minus F2, F1 minus F2 whole square times ln 1 over delta, then your success probability is at least 1 minus delta. Sure. And it does not depend on M. It is not trivial analysis, because as I said, if you use usual union bound, there is something called union bound, then you will get another log M term, but there is a sorry, but there is a way to get rid of that log M term. Sure. Question before we move on to our next topic. Okay, so what's the time? Can anyone? Oh, this is good. Okay, so let me introduce to our next topic, and then we will continue after lunch. So our next topic is sampling, not sampling, streaming. Okay. So what we usually assume is that we are given an input, and we want to which we can store in a memory, and then there we can run our algorithm and compute the output. That is the usual model of computation, which is called RAM model of computation, by the way. Whereas there is another model which is called a streaming model, where the model is the inputs are coming as a streaming fashion. It's like keep on coming. Think of an internet router which just observes a stream of IP packets all over. It's just sure, and it wants to compute something, some function of all the IP packets. So yeah, that's a good example. So think of these are IP packets, and here is the router. So this is a very classic example where, for example, it wants to compute which IP address has the most number of IP packets, right? Or so that will correspond to which websites are getting visited highest number of times. Or it may want to compute which IP address has, so each IP packet has various fields, but at least it has two important fields. One is, say, source IP packet, source IP address, source IP, and another is destination IP. Sure. Source IP tells from where the IP packet came, and destination IP address tells where it will go. So, for example, think of the router who wants to compute what is the most frequent destination IP packet, IP address. That will correspond to what are the popular sites, popular web pages that people in the network are visiting. Maybe Google's IP address will have most highest number of packets, because whenever we search, it goes to Google servers and so on. And whereas, for example, source IP address, so maybe the institute want to monitor which users are using most bandwidth and bandwidth hogging, and so then the job is to find those source IP addresses which has most number of IP packets. So if we download movies, that amount to lots of IP packets, and many IP packets will have source IP address from those machines who downloads many movies or downloading many data and so on. So, but the idea is that it wants to, so for this problem, what is the input? Input is all IP packets that it is seeing for a day in 24 hours maybe, which can be billion or trillion, right? Not only that, IP packets just come and go. It's not possible that let's store all the IP packet in some hardware, and then at the end of the day let's compute something. It doesn't have so much memory, and it's not feasible. So it has to, so IP packets will come and go, and it can see every packet at exactly one, and it needs to compute some functions on it, maybe maximum frequency, minimum frequency, and so on and so forth. So this is the streaming model. So what are the most interesting features of the streaming model? Input is available in streaming fashion, not feasible to store all the input, and that's it. These are the main two functions. And what do we want? Want to compute various functions of the input stream. Sure. Is the model sort of clear? So you can keep this example in your mind. That's a sort of model example. Of course, there are other examples. You can think of very large database systems. So usually, if your volume of data is large, if the volume of your data is large, it is not residing in your RAM. It is residing in a magnetic tape, right? And those devices are inherently sequential devices. Now you can, of course, access those randomly, but if you access those sequential devices randomly, then the devices, your access will be very slow. On the other hand, if you access the data sequentially in the sequence in which the data is residing on the tape, then those devices are pretty fast. So if you have large data, terabytes, petabytes of data residing in a magnetic slow memory, slow if it is accessed randomly, but it is reasonably okay if it is reasonably fast if it is accessed sequentially, then there also you can use these streaming algorithms. You can think of, you can put a restriction on yourself that I have to see the data in a streaming fashion, right? And then these kind of problems make sense. Now, our first sort of problem in this case, which I won't tell the answer now, we will tell the answer after the lunch break. Let me pose the problem, is that in the usual case, in our sampling case, we just told that sample 1 vote uniformly at random. And when I say that, we sort of assume that if there are n votes, I have a sort of n-sided dice with which you can just roll and sample 1 vote uniformly at random. But suppose I am given a stream of n things, and I want to tell you, I told you that that I want to sample one of this item uniformly at random. So input is, say, input is stream of length n, stream of n items, and output is an item sampled uniformly at random. Any idea how can we sample a item uniformly at random? There are, so think of that, there are, say, n items, item 1, item 2 and so on, there are n items, and I keep seeing, or let me write this way, and these items are coming to my device in a streaming fashion, and I want to sample one of this item uniformly at random. So here is a simple trick. So you know there are n items, you first decide uniformly at random which item to pick, right? There are numbers 1 to n, you uniformly pick one number, say 10, and then just throw first 9 items, pick the 10 item. Fine, everyone with me? Don't look at the stream, you know what are the number of items n, and pick a random number from the set 1, 2, 3 up to n, and just pick that item. No, my objective is to output an item which is selected uniformly at random. That's it. That's my objective. So I'm done. What if I don't know n? If I don't know n, this strategy doesn't work. And it's not at all clear. I may know n at the end of the stream, but at the end of the stream, if you tell me to pick item number 10, I haven't stored that item number 10, it's already left. How can I output item number 10? At least it doesn't seem obvious to me. How can I output item which is selected uniformly at random from the input stream without knowing the length of the stream? And look, such a fundamental task is already becoming non-trivial in the streaming model. The task is so fundamental that in the classical model we are not even worrying about it. We are just saying go and pick. In the streaming model, it's already non-trivial. We don't know how to do. Of course, we will know after the lunch break, but this can be an appetizer for your lunch. can think about this. How can we do? The problem here is you are given n items, item 1, item 2, item n in a streaming fashion, and you want to output an item, say item I. So you want to output an item, and which should be item I with probability 1 over n, which should be item j with probability 1 over n. That's it. So if you know n, you can choose a number 1 from the set 1, 2, 3 up to n uniformly. That means you pick I with probability 1 over n and output the ith item. So the probability that you output the ith item is 1 over n. The probability that you output the jth item is 1 over n. So the output distribution is uniform over the input. Now I'm asking you to do the same job without knowing n. They are coming. Yeah. So for example, you can assume, okay, so what power do you have? This has some memory which can hold, say, constant number of items. You can of course store 10 items, 20 items, 50 items, 1000 items, but you can't store n items. Sure. So usually it's assumed that you can use big O of log n items, log n bits of memory. Look, this much memory we need because to write item I, and there are n items, I need log n bits, but I am asking you to use only that much space up to constant factors. So you have big O of log n bits of memory, and with that you have to output an item which is distributed uniformly at random from the input stream without knowing n. Okay, sounds interesting, sounds like an interesting problem. Item can be item I, maybe you can output item 1, item 2, but I will say your algorithm is correct if the probability that you output item I is 1 over n. It has to be exactly 1 over n. That's what we mean by sampling uniformly, right? Yeah, so think of this, these are item 1, item 2, call this if it helps, item 1 to item n. There is no same item. So think of these are Aadhaar IDs, there is no repetition. So what? Sorry, whatever item you pick. Yeah. So what is your algorithm? For example, suppose you first see item 1, first item. What will you do? So the problem is you can't keep all the items, right? Maybe I'm not saying it properly. So at the end of the stream, so for example, you can say that, okay, I'll always output item 1, first item, right? Then that's not a correct output, because you are always the probability that you are outputting first item is 1 and the probability that you are outputting item 2 is 0. So that then your algorithm is wrong. That your algorithm is not meeting my requirement that the item should be sampled uniformly at random. You can of course say I will always output say 10th item, but then the probability that your output is 9th item is 0. The probability that your output is 10th item is 1. Then your output is not a uniform sample from the input. Give me an output which is uniform over the input. So think of every item as a Aadhaar ID. Yeah. So and suppose your output item 1, then it is always output item 1. Then it is not a uniform sample. It's distinct, okay, but it's not uniformly sample. It's not uniformly distributed over the population. Just compare it with the result if of the algorithm if you know n. What is the algorithm if you know n? First you select a random number from 1, 2, 3 up to n. Suppose you pick the number I. What is the probability that you pick I? Is 1 over n. What is the probability you pick j? Is 1 over n. Once you pick a number I, output that number item. If you pick I, output ith item. If you pick j, output jth item. So what is the probability that you output ith item? Is 1 over n. What is the probability that you output jth item? Is again 1 over n. No, you just throw. You just count. Suppose my number is 100. I just don't see. I just need to output say 100th item. Why should I store item 1, item 2 up to item 99? They are of no use. I'll just throw them. And whenever I 100th item will come, I'll just output 100th item. Isn't it? So just imagine I need the same kind of output without knowing n.